Hi, my name is Liam, and welcome to my first ISP. So what I've made here is what I'm calling the matrix graphing calculator. If I turn it on with this switch here, you'll see that it displays a line on that 8x8 LED matrix and also displays the slope on the two 7-segment displays. So if I move this potentiometer here, you'll see that the graph moves in accordance with the slope on the 7-segment displays. As you can see here, some problems do arise when you divide by 0, but that's just normal because dividing by 0 is bad. This video is the long form video of this project because I didn't feel like I could say everything that I wanted in 2 minutes. So I decided to make a video with less time pressure, but I'm still trying to keep it pretty concise. Let's begin by talking a bit about LED matrices. We already know how these things work on the inside, but we don't know how to run them yet. Say for example we wanted to turn on this green pixel. We know that we'd have to turn on row 3 and column 3. Now say that we wanted to turn on this pixel, but we also wanted to turn on this pixel. Then we'd have to turn on this row and this column, but we'd also have to turn on this row and this column. What would happen is that there would be overlap of power on ground on these two blue pixels, and they would also turn on, and this is not what we want. So we have to find a way around this. What we can do is turn on one pixel at a time, and then draw the line, but with one pixel. And what happens if we speed this up is that it becomes less and less noticeable that there's only one pixel until eventually it seems as if the whole line is on at once. This technique is named multiplexing, and it makes use of an optical illusion in persistence of vision. Our next step is to find a way to turn a slope into a set of instructions to control our LED matrix. Luckily, to do this, there's something called a line algorithm. Let's take a look at a famous one. It's called Bresenham's algorithm. What Bresenham discovered is that a pixel can only be one higher or on the same level as the pixel before it. Now this is assuming that the slope is under 1, but if the slope is over 1, the opposite is true. X can only be 1 greater or the same. He also discovered that if you draw a line between the vector slope and the point, the length of that line tells you where to draw the next pixel. We'll call that line error. The error is equal to the length of that line plus the previous error. If the error is greater than 0.5, we move the pixel up 1. If the error is less than 0.5, we keep the pixel on the same level as the previous pixel. The error does not reset between pixels, but if you move the pixel up 1, you subtract 1 from the error. On the screen right now is a comparison of Bresenham's algorithm and my algorithm that I'm using for my graphing calculator. The main difference is that for mine, I input a slope where he gets the slope with two coordinates, so a starting coordinate and a finishing coordinate. As well, I calculate y based on x or x based on y, whereas he determines whether or not to move up the pixel. While I didn't end up using Bresenham's algorithm, it was still really helpful in building my own, so I decided to include it. Here's a short animation of my algorithm. Basically, what it does is it solves for y for every x, and all these dots are going to be pixels that are on the matrix. This is for the slope that's under 1, but if the slope were over 1, we'd be solving for x with the y instead of y for x. The matrix takes in 16 inputs, not sets of coordinates, so we have to convert these coordinate sets into inputs for the matrix. It's actually pretty easy to do this. All we have to do is bit shift 1 by y or x. As you can see on the screen, if we bit shift 1 by y, we'll have 7 zeros and 1 1. That 1 will be in the yth bit of the 8-bit number. We do the same with x, except we have to then not it because we need 7 1s and 1 0. With that, we can now display positive slopes on an 8x8 LED matrix. Thank you for watching.